Welcome back to CSAI Think Tinker Learn. This is part of my System Design Essential series. The goal here is to give you a solid mental model of system design topics. We are breaking down gRPC and streaming mechanics today. This is a concept first introduction to help you build your system design foundations quickly. If you want to see a deep dive on the trade-offs or a specific case study, let me know in the comments. No fluff, let's get into the technicals. Please remember to like, share and subscribe to support this new series. And if you are more of a reading kind people, there are certain articles that are available on the GitHub pages. This is the site. You can actually view all the hyperlink articles are currently available. The link will be in the description. So let's get under the hood for gRPC. The core reason gRPC is so performant is it's moved from text to binary. In a standard REST API, we waste bytes on verbose text keys like user ID, timestamp, and so on. gRPC uses Protobuf, which replaces these with deterministic numeric tags. It also uses Varint encoding. Small integers take up only 1 byte, whereas JSON wastes space storing them as strings. A deterministic binary grammar yields payload 3 to 10 times smaller than JSON, making serialization proportionally faster. We do not ship empty space, we ship raw efficiency. The secret sauce of gRPC is the HTTP2 engine. Legacy HTTP 1.1 suffered from head of line blocking, where a single slow request could clog the entire pipe. HTTP2 fixes this with multiplexing, a multi-lane highway where different streams interleave over a single TCP connection. We also get a binary framing and HPAC compression to squeeze metadata. Crucially, HTTP2 includes flow control, which acts as a throttle to prevent a fast sender from drowning a slow receiver in data. To understand the architecture, you must distinguish between stubs and channels. Stubs are the general interfaces that hide the networking entirely. Calling stub.getReport feels identical to a local function call. Channels are the physical connection manager that handle TCP states, load balancing, and the TLS. Here is a vital interview insight. In production, you create one channel and spawn multiple stubs from it. Do not rebuild channels per request. The TCP handshake overhead will kill the entire latency. Gear 1 is the Unary RPC, the Bedrock pattern. It's the gRPC equivalent of a standard REST GET or a POST. One request, one response. It's perfect for discrete operations like authenticating a token. However, beware the failure point. If you try to loop unary calls to fetch millions of records, you will exhaust memory and time because the system has to buffer the entire result set before moving on. For large data, we need to switch gears. Gear 2 is server streaming, also known as the fire hose. The client asks once, and the server pushes incremental data frames as they become available. This is perfect for real-time stock tickers or large paginated exports. Under the hood, if you're using Python, a simple yield generator handles the framing automatically. The warning zone here is the memory spikes. If you don't respect HTTP2 flow control, an unthrottled fire hose will overwhelm a constrained client's RAM. Gear 3 is client streaming, or the collector. This uses lazy evaluation to upload massive datasets, piece by piece. The client streams items one at a time and receives a single summary acknowledgement only at the end. This is exactly how you handle a 10 GB file ingestion or a batch IoT telemetry without ever buffering the entire payload in the client's memory. Items are generated, framed, sent, and freed from memory iteratively. Gear 4 is bidirectional streaming, the full duplex mode. Here we have two independent simultaneous streams where neither side waits for the other. This enables the interactive communication like multiplayer game states or collaborative editing. The failure point to watch out for is the race conditions. Because these streams are fully independent, your application code must be robust enough to handle out of order logical processing. Do not assume requests and responses will align sequentially. How does a continuous binary stream know where one message ends and where the next one begins? The answer is length prefix framing. Every message starts with a 5-byte header, 1 byte for a compression flag, and 4 bytes for the length prefix. The receiver reads these 5 bytes, knows exactly how many bytes to read for the payload, processes it, and then immediately grabs the next 5-byte prefix. If it is a fluid, self-describing stream that avoids the passing overhead of text-based delimiters. Here is a classic senior interview trap, the HTTP 200 trap. gRPC almost always return HTTP 200 at the transport level, even if your application throws a not found error. Now, this is because the HTTP status is logged in when the connection opens. The true application status, one of 16 gRPC status codes, live in the trailers sent after all the data frames are finished. If you tell an interviewer that a missing gRPC resource returned HTTP 404, you have missed the point of how gRPC utilizes HTTP 2. For cross-cutting resilience, gRPC uses deadline propagation. Instead of a simple timeout, clients declare an absolute time budget. This deadline propagates automatically through the headers frame to all downstream services. Service B doesn't get the original 5-second budget. It inherits the remaining time left after service A is done. This fixes the cascading hang problem found in the early REST architectures, where downstream services would hang indefinitely, blocking the entire system. gRPC also features a middleware layer called interceptors. This allows you to execute logging, metrics, and auth checks without touching your core business logic. Metadata, the gRPC equivalent of HTTP headers, is used to pass key value pairs like trace IDs. An important implementation detail. If you are sending binary metadata, the keys must end in dash bin. The framework detects this suffix and handles the base64 encoding and decoding automatically over the wire. When comparing REST versus gRPC, remember that REST is built for public-facing flexibility, while gRPC is for internal high-performance rigor. gRPC wins on payload size, requires schemas, and native streaming, but it has a major drawback: browser support. Browser cannot speak gRPC natively because they lack access to HTTP2 trailers. To use gRPC in a web app, you must use an Envoy proxy or gRPC web adaptation layer to bridge the gap. In a system design interview, use these mechanics as your blueprint. If asked for analytics pipeline processing, 1 million requests per second, choose bidirectional streaming plus multiplexing. For a 10 GB file ingestion, specify client streaming to avoid memory buffering. For a system prone to hangs, highlight deadline propagation. Memorize these architectural translations to demonstrate you understand not just the what of gRPC, but how of high performance networking. The gRPC philosophy is simple. Contracts are not optional. Transport matters, and streaming is a first class citizen. When you write stream in a .proto file, you are deliberately designing the physical flow of your data. Now for today's question. In your own microservices, have you found gRPC's strict contract first approach to be a benefit, or does the overhead of protobuf generation slows your development down? Let us know in the comments. If you enjoyed this article, please like, share, and subscribe to CSAI Think Tinker Learn. Check out the full series on our site, and I'll see you in the next one.